So we've just discussed the importance of the pyrimidine and the purine bases. And we talked about how these things are going to start connecting together to give us nucleosides and then nucleotides and then nucleic acids. All right, so this is the screen that we left off on. And we said that we can have multiple phosphate groups on these things. And the number of phosphate groups can be embedded into the name, so diphosphate, triphosphate, monophosphate. And we really related this to metabolism and energy that your body needs. So we can start ripping off these phosphate groups one at a time. We can release a little bit of energy, and away that we go. Okay, so we said that these are the building blocks of the DNA, or what will be the DNA molecule. But we still have to talk about connections. We still have to talk about how these things are going to hook up the way that they're going to. And one of the first things that we have to discuss is that they have a particular order that they will connect in. And we call this the 5' and 3' end. Okay, so what does that mean? Well, if I take a look at the 5, then this typically in organic chemistry is the number of carbons in the long chain, right? Okay, so we know that this is a heterocyclic ring. We know that there's other things besides carbon there. So it's at the 5 spot somewhere. It's at the 5 spot. The 3 is going to be the same reason. This is going to be at the 3 spot. So I've got a 3 spot and a 5 spot that's going to be very important. Notice here at the very top, though, we also have this little apostrophe, and this is what we call prime. And that, I've already referenced to that before, that is because we have more than one ring. We have a ring from the base, and then we have another ring involved in the sugar. So we're going to have to look at the primes, which is the sugar piece, and then we're going to have to look at the 3 and the 5 position. So where are those located? Well, those are located here. So this is the ribose, and this is the actual ribose form of the sugar, and the reason is because I see the OH group down here on the number 2. So if we look at where the base is going to attach on the ring, right, here's the base, so this would be my A, T, G, or C. That base is attached to this particular carbon. This is where we're going to start spot number 1. So this is what we're going to call 1'. And then 2' is the OH that could be kicked off. And this is why we were calling this 2-deoxy, right? Because it's letting me know which of the OH groups have been removed. 3' is going to be on the 3rd carbon around the ring. And this is going to be an important carbon. All right, because we just said that if we go back to the previous slide, this is going to go from 5' to 3'. So we know that 3' is going to be important. So I'm starring that one. So 4' will also be in the ring. And then 5', this was the longest carbon chain. It just doesn't happen to be in the ring. So 5' is going to be up here. All right, so those are the 2 carbons that are drastically important when DNA becomes assembled. 3' and 5'. All right, linking up. We just identified the 3' and we just identified the 5'. So at the 3' carbon, that OH group that was located there is actually going to leave. It's going to poof, disappear. And we're going to get a site of attachment that opens up at that spot. What goes there? Well, it's a phosphate group that goes there. And that phosphate group is coming from another molecule. That other molecule is actually, in this case, another nucleotide. And that nucleotide has a phosphate group, and that phosphate group is attached to the 5' carbon. And that is why we say 3' and 5' are going to be the most important carbons in the DNA chain, because that is what begins to link these things up. Okay, so is there a picture? Yeah, I've got one. Here it is. this is better than me drawing it, right? So if you look at the way this structure is drawn, here at the bottom is my ribose ring, and it's actually ribose. And then the 3' is identified. But this is, let's pretend, our very first sugar. At the very, very end. Nothing else comes after this. That's fine. So at the 5', this is where the phosphate group came off, right? Right there. So there's the 5' position. Well, that phosphate group is going to attach to another, basically base, on a sugar, and it's going to attach at the 3' position. And then that phosphate at 5' goes to 3', and that phosphate at 5' goes to 3', and this phosphate at 5' will eventually go to a 3' sugar. This is what we call our sugar backbone of the DNA molecule. Okay? So sugar, phosphate, sugar, phosphate, sugar, phosphate, sugar, phosphate. That is the way that it is ordered. And all of those sugars are connected through a phosphate group. Every single one of them down the line. This is our sugar backbone of DNA. On the other side, to the right-hand side of this, you're seeing them identify the bases that are coming around here. Now, typically, U would have been T. If this was DNA, this would have been a T and not a U position. U is only found in RNA, and we know we have RNA because we have the OH groups that are there. If we did not have an OH group there at all, period, we just erase it, this would then change to DNA. That is my 2-deoxy form. And this U would have had to been a T if that was the case. So just a slight difference. That's really all that we're after. So here's another example. Sugar, 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 sugar. And then this maybe could continue on. I'm just not really sure. The picture doesn't really lead me to believe that, but I think it probably does. DNA is more than just 5 sugars or 5 base pairs. We typically have thousands and thousands and thousands of them. Phosphate is the connector piece between all of the sugars. And of course, this up here is the 5' end. And this down here is a 3' end. If I go back to this diagram, notice how they've drawn the bases over on the right-hand side, and they kind of make them point straight out to the right. So, in a quick diagram, that line would represent my sugar backbone with the phosphates. I've just gotten really lazy here, and I didn't draw anything else. And then my bases will typically point out like this. So maybe this is an A and an A and a T and a G and maybe another G. Who knows what's there? That's where we all become different. How are the base pairs ordered up with each other? Well, we also said that these base pairs have to be paired, right? They have a particular preference that they like to be paired up with. All right, so I'm going to change the color here. And the G will typically be paired up with C. And that G will have a C that's paired. This T will have an A that's paired with it. That A will have a T. And this A will have a T. And you know what? Those bases are just not free. They're just not swimming around. They're actually also going to be connected by another sugar backbone strand. And this is where we have our normal, what we would like to call our DNA ladder, but you got to be careful because DNA ladder also means something else in the laboratory. And the reason they're calling this as a ladder because it kind of looks like one, right? We have one part of the ladder here, one part of the ladder here, and then we have connector pieces that are in the middle. And those connector pieces are involved in hydrogen bonds. We know how many hydrogen bonds, 2 for every AT, 3 for every GC, and those hydrogen bonds is the glue that's going to keep this strand and the second strand together. Well, here's another fuller picture of that. There's a lot of stuff here. But this is more of a full-bodied chemical structure of how the DNA is going to start to look. It's a very complicated, beastly type of molecule. Again, I see my sugar backbones. There, 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 and there. On one end, we call this the 3' end. This has my OH group on it. That's connected with a phosphate, a phosphate, a phosphate, a phosphate. And then let's say it does really stop there. This is the 5' end, where my phosphate is at. So 5' end is always going to be the phosphate end of a DNA, and my 3' end is always going to be the OH end of the DNA chain. On each one of those sugars, we have a base, and they're labeling it for us, at least in this first one and at the top one. We have the G base, that's right here. That is complementary. I see the OH bonds that get formed here between my bases, and this is connected to cytosine on a different strand that hangs out due to those 3 bonds and these 2 hydrogen bonds and those 2 hydrogen bonds and these 2 hydrogen bonds, or actually there's 3 right here. They'll go on and on and on. Super glue. These chains are not going to be ripped apart very easily. So this gives you maybe a better idea of the lead up to the DNA structure. We are now putting all of our pieces together, little bit by little bit by little bit. And this is what we're going to see. Again, a lot of times we don't need all of this detail. We just need to draw a straight line that represents our sugars and our phosphates. And then off of this straight line, we will write the abbreviations for the bases that are attached. However, you're going to see chemists get even lazier than this. And they will eventually drop the entire line altogether. And they will just write out the base pair orders in a line straight across. And we have to assume that we know all of the other pieces that are going to go on. We have to assume that we know there's phosphates that connect them, that these bases are attached to sugars, that they are the deoxy form if this is DNA, so no OH groups at all, and that's what this was. Look, no OH groups on any of these sugars all the way down. And we have to imagine these pieces in our head to get a fuller picture of the DNA structure. And a lot of people just skip that part. A lot of people look at these base pairs and they just see a bunch of letters and they say, what do these letters even represent? Well, now you know. These letters are representing the bases. These bases are either pyrimidines or purines. They come in 4 different forms. They are connected to a ribose ring, and that ribose ring could be a deoxy form in the version of DNA. And those rings are then connected by phosphate groups that hold all of these bases together, one after another, after another, after another. If I was in a biology class, they probably wouldn't go through all of that detail. They would just say, listen, here's the DNA, and it has 4 base pairs, and it's A, T, G's, and C's, and the order of them are going to be important. There you go. And that's it. But there's more to the story than that. So a couple of other things that I want to tell you about before I end this video. And number one is the order. Things have to be systematic, right? We know that we now can draw this line, and the base pair ordering is pretty important, but what order do we actually write those down in? So all polynucleotides, that's what you're seeing at the first lecture note up at the very top. Poly means many, nucleotides, of course you now know what that means, or nucleic acids, are written with the 5' end on the left and the 3' end on the right. So this is the normal order that we go in when we write down these bases. So if I go back to this previous screen, one of the reasons that I did this is to kind of prove a point. Here is the 5' end, which is the phosphate end. We call that the head of the chain. And the 3' end is going to be here at the bottom. That is the OH group. The OH group is the tail of the chain. So the order of these bases are very important, and I have to write them in order of 5' to 3'. And what I did down here was not do that. I actually kind of went backward, didn't I? Let's see. No, I thought I did, but I did not. So here we basically see, oh, well, this was my example. Right here was my example, and then this is what I flipped. So let's use this example that you're seeing on the screen. As we go down through, the A is on the 5' end. So when we write these bases down, we would actually start off with A. And then we would write the base letters all the way through the chains until we get to the very end. And this is the 3' end. And this is my G for guanine. So here is the representation of what we would do here. If this was my 5' end and this was my 3' end, then what I have done here is that I have written it backwards. This is not proper. I need to go 5' to 3', and I need to write the letters in that order. So G, T, T, and then finally A. So there is an order to all of this madness. The sequence of bases are written down with their one-letter abbreviations most of the time. Again, U is only used for RNA, and we're going to be focused on DNA mainly here. The ending base gets a P that's typically put onto the end, and this shows you that this is an ending pair, all right? So, for instance, ATGC, and then I would write down AP. That is a very strong sign that G is the last one in the chain, fully the last one, and that this is not a piece of the DNA molecule somewhere in the middle. It's actually at the end. The D in front, the D typically can be placed in front of the base pairs, and this is just a confirmation that you are working with DNA and not RNA. So if you do see these letters, don't let them throw you off. That's what that means. This DNA, we're working with DNA, and this one, we are at the end. That is a true end to the DNA molecule. So here's another example of maybe what you would see. 5' to the left, 3' to the right, and then we just write a bunch of letters in between, and each one of those represents the bases, either the purines or pyrimidines that we are working with. Guanine, cytosine, adenine, thymine. So this is what we call our primary structure, the primary structure of DNA. Right here it is. We have gotten lazy. We have basically thrown off the sugars. We've thrown off the phosphates. We don't even show those in the diagram or the depiction, and we're only writing down the order of the base pairs, which is actually the most important piece anyway. So in the next video, we'll come back. We'll continue with this discussion. We'll get more familiar with the DNA structure, and we'll continue to go on and on and on to see how far we can take this.